Assalamu alaikum. Inshallah, in this video we'll start our tutorial about extension springs. First, the difference between extension springs and compression springs. That extension springs carry tensile loading. Yani in compression springs we applied a compression force and we compressed the spring. But here in extension springs we do the opposite. We will have a tensile force that will tension or extend the spring. By applying this load, we need to, in order to apply this load, we need to have a hook. So that is the second difference. First difference, that we have a tensile loading, we apply a tensile force, and we apply this tensile force on a hook. And also there will be no distance between the coils. As you can see here, the coils are in contact with each other. In order to maintain this contact, or to maintain no distance between the coils, we will apply an initial tension. Okay, so the spring is under initial tension already before we apply our tensile loading, our force F. Okay, why we are doing this? Because the spring manufacturers prefer some initial tension in closed-wand springs. The meaning of closed-wand springs, that when extension springs are made with coils in contact with one another. That is the meaning of closed-wand. So if you find any question that mention a closed-wand, he means that the coils are in contact with one another. Okay, in order to maintain this contact, we must apply an initial tension. And this initial tension will maintain this contact in order to find or to hold the free links more accurately. Okay, the free length is this length from here, from this point to this point. Why exactly from this point to this point? Because we apply the load at this point. Okay, at this point from the hook. That is the free length. Okay. Let's see a question about the extension springs. Here he said a hard run. Hard run, usually in the question he will give you the manufacturing process or the heat treatment process that is applied to the material that the wire is made of. Okay, this information that it is hard run, we will use it in order to find different things that we will see during our solving, inshallah. Okay, you'll find in table 10.5 that this word HD means hard run. Okay, and you will find again hard run here in table 10.4, and you will find cold run, okay, or hardened at this table 10.7. So this information that it is hard run steel will help you and find different things in these three tables. Okay, so in these three tables, so we have table 10.5 and 10.4 and 10.7. Let's see how we'll use them, inshallah. Okay, he said it is extension spring, so we know it is extension spring. Has a wire diameter. The wire diameter is this diameter we represented by small d. Okay, so d small is equal to 0.035 inch. Okay, and an outside coil diameter. Coil diameter are these are the coils. Okay, when you say outside diameter, we means that we will start from the end here to the end. Okay, that is the outside diameter of the coil. Okay, so from the highest point here to the lowest point here. Okay, so the outside diameter OD is equal 0.248, and the hook radii of R1 is equal to 0.106 inch and R2 0.089 inch. The hook radii, you can see it in this photo. Okay, that is the hook. Okay, from different views. R1, you can see it is D over 2. And what is D? D is the mean diameter. Mean diameter means from the middle of the wire or the center of the wire to to the other center, okay, that is the mean diameter, okay. And the mean diameter here, if we want to represent it, it is from here, from here, okay, from this point to this point, that is D, okay. So R1 is equal to D over 2. It is from the center of this circle, okay, the center of the hook to the center of the wire, okay, that is R1. R2 is the radius of this curve here, or this curvature here, okay. So it is from the center, or from this center of this, of this semicircle or this quarter circle, to the center of the wire, okay, that is R2. So he gave me R1 and R2, and an initial tension of 1.19 pound force. We said at the beginning that we apply initial tension or preload, okay, sometimes we call it preload, in order to maintain a contact between the coils, okay. So we represent it like Fi is equal to 1.19 pound force, okay. The number of body turns, when he said body, he means the coils, okay. That is the length of the body. These are the coils, so the number of them, if you count them, that is the meaning of the number of body turns, okay. It is 12.17. so this is MB, number of body turns, in B for body, okay, is equal to 12.17. From the given information, determine the physical parameters of the spring. What is the meaning of physical parameter of the springs? The physical parameter of the springs contain the nomenclatures parameters, the dimensions parameters, and the parameters that it is related to the springs, the diameter of the coil. C is the spring index, which is the ratio between the diameter of the coil over the diameter of the wire. B is a correction factor for the curvature, okay. In the book we usually use this Briggs-Strasser, or whatever you can pronounce this name, okay. KB to represent the correction factor for the curvature. We don't use KS and KW. KS and KW, you can find them in the equation sheet also if he told you to use them, okay. And these are the equations for to find them, okay. So in order to account for the curvature effect, because this curve will cause a stress concentration, in order to account for this we will have a correction factor, okay, which is KB, and it is equal to 4C plus 2 over 4C minus 3. So as you can see, it is a function of the spring index, which is a measure of coil curvature, okay. And the spring index, if he asked you if it is in the preferred range or no, it must be between 4 or equal, larger or equal to 4, and less than or equal to 12, okay. So that is also one of the physical parameters of the spring. NA is number of active coil. The number of active coils is equal to the number of body coils that is given in the question, over the ratio between the modulus of rigidity over the modulus of elasticity. L naught of first K is a spring constant, okay, from physics. This is the equation that we will use to find the spring constants. They call it sometimes spring rate, sometimes also it has other name, scale of the spring, okay. It is equal to D power 4, the diameter of the wire. G it is the modulus of rigidity. We will see how we can find the modulus of rigidity and these other things. NA is equal to MB plus G over E. Y max is the deflection, okay. We will see why we call it max, okay. L naught is the free length, okay. The free length, this one is from this point to this point is the free length, so free length is L naught, okay. So at the beginning it will be L naught, then you will apply extension force or tensile force, then it will be deflected by a value which is equal to Y max. So L, the final length, will be L naught plus Y max. and this is the equation to find L naught. So that is the meaning of when he asked me to find the physical parameters of the springs of the spring. Okay, so let's find one by one. Okay, in order to find let's write them here. First, the physical parameters: D, C, KB, NA, K, L naught, Y max, and L. Okay, D is the mean diameter. Okay, mean diameter D. Okay, sorry, D capital. Okay, as you can see, this one is the outer diameter. It is OD. So the difference between them is this distance, this small distance from the center of the wire to the end here, and this distance also. This one is D over 2, and this one is D over 2. Okay, so the addition of them is D small, which is the wire diameter. Okay, so if I want to find the D, the mean diameter, it is equal to outer diameter minus the wire diameter. And I already wrote this equation here. Okay, usually you will be given the wire diameter, and if you are not given the wire diameter, just assume a value, small value, and of course it will not be larger than the coil diameter. Okay, assume a value, and it will be outer diameter minus the small diameter. And if he give you the inner diameter, then you will add the wire diameter in order to find the mean diameter. Okay, so D is equal to outer diameter minus minus the wire diameter. The outer diameter is given in the question 0.248 minus the wire diameter is 0.035. So this will give me 0.213 inch. Okay, for C, the spring index, it is the coil diameter, the mean coil diameter over the wire diameter. Okay, this is 0.213 over the wire diameter, which is 0.035. Okay, this will give you that the spring index is 6.0857 inch, and it is in the preferred range because it is between 4 and 12. Okay, the preferred range is between 4 and 12. Now let's find KB. KB, we find it because we want to account for the effect of the curvature effect or the stress concentration, and then we usually multiply it by F max or the force, or the shear stress. In order, when we count or calculate the stress, we also make consideration for the curvature effect or the stress concentration. Okay, so KB is equal to 4C plus 2 over 4C minus 3, 4 times 6.0857 plus 2 over 4 times 6.0857 minus 3. Okay, this will give you 1.23427. Okay, the next we need to find NA. Okay, number of active coil. So number of active coil is equal to MB, number of body coils, plus G over E. Okay, number of body coil is given in the question. G over E, we want to find them using the table. So we know that the manufacturing process that we have for this material is hard drawn. So I will use this row. Okay, this row, as you can see, contain different range depending on the diameter in inch. Okay, so if you are given the question in SI unit, you have to convert it to be in inch. If you are given the wire diameter in 25.4 millimeter, يعني in millimeter, you have to use this conversion factor. Okay, you will divide by 25.4 in order to get in inch, because the table is only in inch. Okay, so already our question is in inch. Okay, and this is the wire diameter, d small. Okay, my wire diameter is between these two values here. Okay, it is d small is 0.035 inch. So d small is larger than or equal to 0.033 and less than or equal to 0.063. So I am here. So this, that in order to find E and G, I will calculate this value or get these values from this table. I will use this one because I am dealing with not with SI units, with the customary units. So we have mega pound per square inch, 28.7, and for modulus of rigidity G, I will take 11.6. Okay, so let's find NA. We got E is equal to 28.7 mega pound per square inch, and G is equal to 11.6 mega pound per square inch. Okay, so this one is equal to 12.17 is given in the question, the number of body coils. Then the ratio will be 11.6 over 28.7. Okay, this will give you 12.574. And as you can see, 12.7 and 12.74 is near to each other. So this will give you an indication if your solution is right or no, because they must be near to each other. Okay, and I divide them directly because both of them are in the same unit. Okay, they must be in the same unit. Now the next parameter is L naught. Okay, the free length. So L naught, this is the equation for L naught. L naught is equal to 2d minus d plus nb plus 1 times d. Okay, this equation, you don't need the derivation. No one will ask you about the derivation, but if you want to see the derivation, let's ignore the derivation. We can use the equation directly. Okay, so this equation is equal to L naught is equal to 2d minus d plus nb plus 1 over d, and also it's equal to 2c minus 1 plus nb d. Okay, let's use both of the equations and calculate L naught from both of them. And of course they will give us the same number. Okay, 2 times 0.213, this is the mean diameter, minus the wire diameter 0.035. Okay, plus NB is 12.17 plus 1 times the wire diameter, which is 0.035. This will give you that L naught is equal to 0.81695 inch. Okay, and if you use the other equation, okay, L naught is equal to 2 times C is what? C is 6.0857 when we calculated C, the spring index, minus 1 plus the number of body coils is 12.17 times 0.035. Okay, so L naught also will give you the same number, 0.81695 inch. Okay, the next parameter is Y max. Okay, in order to calculate Y max is calculated from this equation, F max minus Fi over K. Okay, Fi is given as a question, it is the preload. Okay, he said 1.19 pound force, the initial tension. Okay, and K is the spring rate. Okay, we also need to find the spring rate. We didn't find the spring rate. It is one of the spring physical parameters also. F max, he didn't mention exactly in the statement of the question, but he mentioned it in part C, which is this load. Why we call it F max, we will see in a moment, inshallah. Okay, So first let's find K, then we will talk about F max. Okay, so K its equation is d power 4 G over 8 d power cubed over NA. Okay, D is a wire diameter is 0.035 power 4. G is the modulus of rigidity. We got it 11.6 megapound per square inch, but we have to multiply by 10 to the power 6 here because everything is in inch. Okay, I want also K to be in pound force per inch, because pound square inch, this one is equal to pound force per inch squared. Okay, and I need my value for K to be pound force per inch because already Fi is given in the question in pound force. Okay, so I have to multiply by 10 to the power 6. So this one will be 11.6, and I will convert it to pound square inch, pound per square inch. This 10 to the power 6. Okay, over 8, 0.213. This is the mean diameter of the coil, times NA to 12.574, and this will give you that the K, the spring constant is 17, or the spring rate is 17.91 pound force per inch. Okay, now we want to calculate Y max. Y max is equal to F max minus Fi over K. Okay, first, why it is F max? We call it يعني F max. It is يعني F in total, but we usually apply it, we consider it at point, we calculate the worst case. We calculate the worst case if you make a section, cross section, if you take this part like this. Okay, here we apply a force, the tension force. If you make a section here, okay, and I will say exactly why at this line, okay, there will be a reaction force. Okay, so if you make sigma Fy equal to 0, then F will equal to F. F in this tensile load will equal to the reaction. So here we will have F also. Okay, the distance between these two, okay, is R1, right? The distance R1, which is equal to the mean diameter over 2. So this distance, okay, is D over 2. This when you have two forces parallel to each other and between them is a perpendicular distance, this will create a couple moment. Okay, this couple moment will, if we draw it, will act or will bend the beam or bend the coil like this, and here he will create a tension. Okay, here will be a tension force in this side, okay, and here will be a compression force. Okay, compression, there is a compression bending will cause a compression in this side and tension in this side. Okay, and we already, when we did the equilibrium on the Fy, or the forces on the y-axis, if we consider this one is the y-axis, okay, this force it is perpendicular exactly to the cross-section area of this coil. So we will have a normal stress, and the normal stress, the force is distributed uniformly around the whole area. So we will have a sigma, or normal stress, which is equal to F over A, and A here is the wire diameter, okay, D. So this one will equal to F over pi D squared over 4, and it's equal to 4F by D squared. Okay, so we will have a normal stress here, okay, sigma n normal stress, and also we have bending stress. This bending stress is type of normal stresses. Okay, we will have tension here, so we have at this point we have to the maximum tension. Okay, because if we draw this line, here we have the maximum tension, and the tension will start to decrease until this point there will be no bending or because you have in the other side compression, okay, and then they will cancel each other, okay. So you'll have something like this, okay. Here you will not have compression or tension, they cancel each other. Here you will have the maximum tension, here you will have the maximum compression, okay. But at the end you have also the normal stress. So the normal stress is distributed uniformly around on the whole cross section area. Here at this side, the right side, it is opposite to the bending stress, the compression bending stress, but here it is added to the tensile bending stress because they are in the same direction. So here you will have the maximum stress, the maximum normal stress. So this point is point A. That is why we called this the force applied here is F max, okay. So that is why it is called F max. And if you derive the equation in order to get sigma A, we will see what is sigma A. Sigma A represent because it is at point A for bending, it is sigma n plus the sigma from the tensile bending, okay. So that is the worst case when the maximum stress will happen here at this point A, okay. That's why it is called F max. So in order to find Y max is equal to F max minus Fi over K. Why it is Fi? Usually in physics we always say that it is F over K. Why we subtract Fi? Because we already have initial tension, okay. We already have initial tension between the coils, okay. So if I apply a force that is already equal to this force, the spring will not expand, will not be tensioned, or will not move or deflect, okay, because already I didn't exceed the Fi. So in order to have a deflection, okay, I have to add a force more than Fi, or the initial tension, and my starting point will be from Fi, okay. That is why we will subtract Fi from our force, okay. So F max is given in part C is 5.25 minus Fi 1.19 over K. We calculate K to be 17.91. This will give you that Y max is equal to 0.2267 inch, okay. The final physical parameter is L, okay, the length after the deflection. It is equal to L naught, the free length, plus the Y max, the deflection, okay. And we call it Y max because it can include the maximum force that we took at this point, at point A. Okay, so L naught is equal to 0.81695 plus 0.2267, and this will give you that L is equal to 1.044 inch. Okay, so let's see part B. We finished part A. Part B, check the initial preload stress conditions. What is the meaning of this? When you apply the initial tension, maybe it is not preferable, or maybe you cannot control this initial tension, or it is difficult to attain. So they made an experiment with respect to the index, the spring index, okay, C, and the torsional shear stress, okay, which is a function of the preload, and they find that the preferred range is this region, okay. So we want to check if our preload is here in this region, okay, or no. So that is the meaning from this question. Check if initial preload stress condition, the shear stress is in the preferred range or no. In order to find this curve can be represented by these equations. That the uncorrected initial torsional stress, uncorrected because we don't know if it is in the preferred range or no, still we want to check, okay. this initial torsional stress is equal to KB 8 FID over pi d cube if it is between this value, يعني it is larger than this value and less than this value, so it is in the preferred range. Okay, so we want to check. So I need to find this value in negative 1000 and plus 1000. Okay, and as you can see it is function of the spring index. Okay, so after we find these values and we compare it to our initial torsional stress, if it is in the between, so we will find we consider it as preferred range. If it is not, so we will say it is not in the preferred range. Okay, so let's find first the T initial anchored. As you can see, all of them contain the KB or the correction factor for curvature. So يعني I can cancel this one for now and just compare them with these equations. Okay, so let's first find our torsional shear stress. So Ti, and it is still uncorrected. We don't know if we need to correct it or no. It is in the preferred range or no. Okay, so it is equal to 8 Fi d over pi d cubed. Okay, so it is equal to Ti preferred or no. That is what we want to find. Okay, so Ti, the uncorrected, is equal to 8. Fi is given in the question 1.19 times d, the mean diameter 0.213 over pi times 0.035, the wire diameter cube, and this will give you the answer will be in pounds per square inch. So 15054.37 pound per square inch. Okay, now let's check if it is between the values in the equation above or no. In order to write this equation, you will have an exponent e power 0.105c in the denominator. Okay, and in the numerator you will have 33500. يعني this one is in the denominator, this one is a numerator. Okay, because sometimes يعني we make mistakes in this when we write it in the calculator. Okay, minus 1000 times 4 minus c minus 3 over 6.5. Okay, and let's check, is my T the initial torsional shear stress, the uncorrected one, is between these two values or no. 33500, also the same value, but we will add plus here instead of the minus. Plus 1000, 4 minus c minus 3 over 6.5. Okay, so if you calculated this one and you substitute c is equal to 6.0857, okay, you will get that this value is equal to 14156.71894 pound per square inch, and the one with the plus is equal to 21207.27 pound per square inch. My value for Ti, the uncorrected, is 15054.3, so it is between them, so it is in the preferred range. Okay, and you can see if you use this graph, this chart, this graph, the spring index C is 6.0857, so something here. Okay, and the value for the torsional stress, the uncorrected, is around 150 okay, or 15. If you see here with psi, it is multiplied by 10 to the power 3, so it is 150,000 something. Okay, it is something here. Okay, so it is in the preferred range. Okay, it is in here, something here, so it is in the preferred range also. So you can check if you have the graph, you can check if your solution is right or no. Okay, so we finish part B. It is in the preferred range. Then the last thing is finding the factor of safety under a static 5.25 pound force load, the Fmax. Okay, here we have 3 applied stresses. Okay, we saw that we have bending stress and normal stress here, and we will call it sigma A. And also we will have, as in the compression springs, we will have torsion stress at the coils, and also we will have at point B, because of the curvature, we will have also torsional shear stress. Okay, so if you see the equation sheet, you will have a factor of safety for the main body, for the coil. Okay, we will call it N, only N. Okay, and it's equal to SSY over tau max. SSY is the torsional yield strength. Okay, and strength is a property of the material. We compare our stress that we apply on the coil, okay, in the spring, to the strength of the or the property of the material. Okay, depending on the tables, we'll see how we get SSY and SY and the strength of the material. Okay, tau max can be found from this equation. Kb is the Berger factor that we already found. Okay, we have everything. We can calculate tau max. SSY, we'll see how we can get it. Okay, we have sigma A. Sigma A is the bending stress and the axial load stress together that we saw here. Okay, the normal stress plus the torsion, the tension stress from bending. Okay, so this one, and we compare it to the yield strength, and also we have at point P here, we will have a curvature. This curvature will have torsional shear stress. We also compare the torsional shear stress that we apply at point P with the torsional yield strength. Okay, so all of them, as you can see, contain Fmax. Okay, and we calculate everything for them except that for Ka and Kb, this K and Kb are function of the radii of the hook. Okay, they are already function of C1 and C2 are a function of the R2 R1 over D. Okay, they represent a correction factor for the curvature Ka and Kb. Okay, so in order to find Kb, you need to find C2, and C2 contain R2. And in order to find Ka, you need to find C1, and C1 contain R1. Then after you calculate Ka and Kb, you go and add them in the equation for sigma A and for the equation for Tb, tau b. Okay, so from where we can get the strength of the materials, SSY or SY or SSY for point B. You will come here for this table. Okay, and this table, in our question we have hard drawn. Okay, so it is near to cold drawn or hardened. Okay, so I don't know exactly what is the manufacturing process, how it is done. Okay, but you can search if you write hard drawn in the Google. Okay, so this table contains 3 columns. The left column is for the body, okay, for the coils. So in order to get the yield strength for the coil, you have to multiply this value. You either take 0.45 or 0.5. Okay, you divide by 100. Don't take 45 exactly, and you take the percentage. That's the percentage from the tensile strength, SUT. We will see how we can find ultimate tensile strength in a moment. Okay. The right one is for the bending, for sigma A. Okay, we here sigma A is normal stress. We compare it to yield strength, okay? But for the point B and point for the main coil, we have a torsional shear stress. That's why we compare it to the torsional shear stress, يعني the shear yielding strength, okay? For the bending at the end, okay, we will multiply 0.75 times the ultimate tensile strength. And for the torsion, but in the end, يعني means at point B, the end of the hook, okay, we will multiply 0.4, okay, times SUT. So how we can get SUT? Also, SUT can be found from this equation, the minimum tensile strength of the wire. Okay, it is equal to A over D bar M. D is the wire diameter. What about A and M? A and M can be found from this table. Okay, here we have the hard drawn wire. Okay, our manufacturing process is hard drawn. Okay, that is the exponent M, and also that is A. We deal with, now our question is in pound square inch, so this value will be in pound square inch. We will not use the SI units. Okay. So let's find the ultimate tensile strength, SUT. Then we can calculate SSY, SSYB. Then we can use this equation in order to find the factor of safety, our requirement in the question. And in order to find them, we have to calculate tau max from this equation, and sigma A from this equation, and tau B from this equation. Okay, and at the end, the overall factor of safety will be the minimum between them, because the minimum means it will fail first. The stress is near to the strength and will cause a failure first in the spring. Okay, so if he said what is the overall factor of safety, so it will be the minimum between them. So let's find the factor of safety. Okay, so the overall system factor of safety is the minimum between NA and NB. Okay, N is equal to SSY over tau max. We compare the shear stress to the torsional shear strength, and NA at point A we compare the yield strength with the sigma A, the combination between the bending and normal stress. Okay, and NB is equal to SSY at point B, the shear yield strength at point B, over the shear stress at point B. Okay, first, in order to find SSY, SY, and SSYB, we need to calculate the ultimate tensile strength, which is equal to A over D bar M. Okay, and A and M can be found from table 10.4. So let's go to table 10.4. At hard drawn, we will have A is equal to 140 and M is 0.19. Okay. So SUT is equal to A is 140, D is 0.035, M is 0.190, and this will give you that the ultimate tensile strength is 264.7 kilopound per square inch, because A is in kilopound per square inch. That's why the value for SUT is kilopound per square inch. Okay, then we want to calculate SSY for the body, and SY the yield strength, and SSY for point B. Okay, all of them is equal to a percentage time SUT, a percentage time SUT, a percentage time SUT. Okay, so what is this percentage? We said it is from table 10.5, table 10.7. Okay, we'll use this row because it is hard drawn, Okay, for SSY we will use the left column, this one, for the body. It will be, you take 0.45 or 0.5 as you like, it doesn't matter. Okay, so we will take 0.45, and here for SY, okay, we will take the right column, it will be 0.75, and for the point B, the end hook at point B, we will take 0.4. Okay, and multiply all of them by SUT to calculate SY, SSY, and SSY for point B. Okay, so it is 0.45, 0.75, and 0.4. Okay, 0.45 times 264.7, and this will give you 119.115 kilopound per square inch. 0.75 times 264.7 is equal to 198.525 kilopound per square inch, and 0.4 times 264.7 will give you 105.88 kilopound per square inch. Okay, now we want to find tau max, sigma A, and tau B. For tau max, the equation is KB 8 times F max D over pi D cubed. We already have everything. We calculate KB at the beginning, so it is equal to 1.23427 times 8 times 5.25 times 0.213 over pi times 0.035 cubed. Okay, this will give you that tau max is equal to 82 kilopound per square inch. Okay, and now I can find N for the body, for the coils. It is equal to SSY because it is shear, okay, in the coils, over tau max, and this will give you 119.115 over 82, and the value will be 1.4526. Okay, and now let's go to NA. It is equal to SY over sigma A. So in order to find sigma A, we have to calculate first KA and C1. So as you can see, sigma A contain KA. KA is for this equation, that is function of C1, and C1 is 2R1 over D. Okay, R1 is given in the question. So C1 first is equal to R1 over D. 2 times R1 is given in the question 0.106. D, the wire diameter, is 0.035, also given. This will give you the C1 is 6.057, and then Ka is equal to 4C1 squared minus C1 minus 1 over 4C1 times C1 minus 1. That will equal 4 times 6.057 squared minus 6.057 minus 1 over 4 times 6.057 times 6.057 minus 1, and this will give you that K at point A is equal to 1.14. Okay, 1.14. And now we can calculate sigma A. Sigma A is equal to F max times K at point A times 16D over pi D cubed plus 4 over pi D squared. Okay, sigma A is equal to F max is 5.25 times 1.14 times 16 times 0.213 over pi D cubed by D is 0.035 cubed plus 4 over pi d squared 0.035 squared. Okay, this will give that sigma A is equal to 156.9 kilopound per squared inch. Okay, now I can calculate the factor of safety at point A, which is equal to Sy over sigma A. Sy is 198.525 over sigma A 156.9, and this will give you 1.265. Okay, now the remaining factor of safety is for point B, in B. In order to calculate NB, we need to find the shear stress at point P. It will have also the same equation for tau max, but instead of this KB, it is another KB, K at point P. This KB is the Berger's factor, I don't know this name, KB, okay, but it is different, okay. There is a new KB, K at point P, yani. Okay, so K at point P is equal to 4C2 minus 1 over 4C2 minus 4. The previous KB is 4C plus 2, and it has 2 and 3, and this one has 1 and 4. Okay, and C2 is 2R2 over D. Okay, so C2 is equal to 2R2 over D. Is equal to 2 times 0.089. D small is 0.035, and this will give you that C2 is 5.0857. Okay, K at point B is equal to 4C2 minus 1 over 4C2 minus 4, and this will give you that 4, it is equal to 4 times 5.0857 minus 1 over 4 times 5.0857 minus 4, and this will equal to 1.18357. And now I can calculate tau B, which is equal to K at point B times 8 F max D over pi D cubed. This will give you 1.18357 times 8 times 5.25, 0.213 over pi 0.035 cubed. Okay, so tau B will equal to 78.6 kilopound per square inch, and then the factor of safety at point B will equal to the shear yield strength at point B over tau B. This will equal to 105.88 or 78.6, and this will give me 1.347. So I have 1.347. I also have 1.265. This is less than NB. Okay, and I have 1.4526. So the smallest value is 1.265. Okay, 1.265 is less than 1.347, and it is also less than 1.4526. So that is the overall factor of safety for me. Okay, and the meaning of this that NA, the minimum factor or the factor, the overall system factor of safety is the minimum between NA, N for the coil, and NB. The minimum was NA. Okay, NA is the overall factor of safety is equal to 1.265. That is the meaning that A at point A, what is happening is bending, right? Okay, there is bending and there is normal stress. Means that the spring will fail because of bending at point A first before point B and point and at the coil, the main body. So yield due to bending of end hook, because point A at the hook will occur first. Okay. In this video we solved the example in the slides or in the book. Okay. In the next video, inshallah, we will solve the only question that is related to our extension springs lectures. Okay, it is also only the question 1036. I didn't find any question that is related to us in the book, all about fatigue, and fatigue is not included with us. Okay, so thank you for your listening.